All right, good morning, everybody. While we're waiting, are there any questions about anything?
I have a question.
Go right ahead.
So when did you want us to start working on a module 2?
Not yet. I haven't sent any videos. I haven't prepped you for it. So I opened it, but don't start on that yet.
Okay.
Yeah, I only opened it so that, I'll know where to go next. But yeah, we'll probably, we still got to do intermolecular forces. Let me actually look and see what's in. I think module 2 is PKA, and we're not doing that yet. Let me open Blackboard right quick. Oh no, I think module 2 is. I'm gonna rearrange those assignments anyway, because some of it we're already doing now. So I got to go in and rearrange the assignments and delete a couple things. So don't do anything with that yet. Just keep following in class, because I think we've already started. Let me see what's in here.
Dr. Russell, do you mind saying one more time what you just said about the assignments? I missed it because my sound was going out.
I was saying in the second module, don't touch that. Yeah, because that's PKA. That's a whole nother topic. We haven't started that yet. We're still really finishing up 1A.
Okay.
Yeah, so with 1A, we still have to discuss. Let me pull this up, because if you go, let me go ahead and share this. If you go to Blackboard, you'll see right here, we've been talking about resonance. We haven't talked about intermolecular forces yet, but I think, did I send y'all Sink or Swim, a video, Sink or Swim, like a little game show thing?
Yes, it's on there.
All right, so yeah, so we're gonna move into intermolecular forces this week, probably Friday, and then finish that. And then functional groups. I know I sent a bunch of functional group videos, but we've been kind of doing those as we come to them. But we got an exercise today that we're going to do dealing with that. And then we'll move to module 2, which is PKA and acidity. So it says second module. So don't do anything in here yet. All right, so we're still doing 1 and 1A. Go ahead. I see 3 hands raised.
I have a question about the problems that we've been doing in class. So are they due today or whenever we take the exam?
You can turn them in a day after, it's fine.
The day after we take the exam? Or?
Yes.
Okay.
So part of that is going in module 1. First module, let me see what's going in here. Let's look at the assignments, and then you'll know exactly what to turn in this one. So in the first module, skeletal line structures, and then that bonding combo exercise that we did. Let me pull that up. It's coming. My computer is very slow. So the problems that we did from here, this is all going to go in that submission link right here. And then there's a little short assignment right here. I'm not even going to go over this because we did so many line and skeletal structures. You can do this on your own and turn it in. It's at that handout we haven't touched yet, but it's actually in this package that we've been working through. I just haven't gotten to it yet. And then in 1A, you can see the topics: resonance, intermolecular forces, which we're going to start Friday. Dipoles, we already talked about that quite a bit, and functional groups. So we're going to do some more resonance and functional groups today. And that handout, let me see what it looks like. So this handout is gonna be, I'm gonna only take this 1A right here. So I'm gonna, that's why I said I wanted to delete some stuff. So it'll just be this. And the other handout I'm gonna delete. As a matter of fact, I can do that now. Because this is more like a, more like practice than it is something that we'll do in class. Because we got a lot of resonance examples in this second handout. And then the extra credit, we're not doing that. So yeah, it's hidden anyway. You can't see that. So, and then the functional group, extra credit. We're gonna do this in class and today actually. So I'm gonna leave it. I said yesterday to a group that I was gonna take it out, but I'll leave it. Yo, all right. So let me delete this problem. Go ahead. I see 4 hands up.
Okay, so we should be doing like, I'm sorry, so we should finish the post assignment for just module 1 right now, right?
No, you can do the post assessment for 1A too.
Okay.
Because the videos that was sent out on Friday, even if we haven't talked about that stuff yet, is not so in depth that you can't touch it. Because all the stuff that's on the post assessment, it came straight from the videos.
Okay, great. Thank you.
Yep. Let me delete this document. Well, actually, I'm not going to delete it because you may want to use it for practice, that problem set 1. But the only thing you're going to turn in from here, from these 2 documents is this module 1A, FCG, IML, solubility, resonance. And yeah, I may have to go in and split that document up because they're 2, or consolidate these 2 submission links instead of just having it separate. But I'll have it figured out before tomorrow, or before Friday when you turn it in. All right. And go ahead.
So the other assignment that you that we've been working on in module 1, plus the little like worksheet that they had in there, and then you said the second link right here that you're showing, and then
we're
the
going to touch that today. We're going to jump on that today.
Okay, so we turn those in
Yes.
by Friday. Well, after Friday.
So we turn in the module 1A and
In module 1.
say again.
First module, you're going to turn in both assignments in there. One of them is you're going to do on your own because it's just drawing skeletal and line structure. So this one, you're going to do that on your own. We've already worked through this. All right. And then 1A, you're going to turn in this.
Okay.
All right. This is, and this we're going to do today because there's a functional group assignment that we can do. This where we pick out the different functional groups. So you're going to turn in, I'm going to combine this into one link so it's not so confusing, but it's only going to be 2 documents that you turn in this module.
Okay. You said only to do the highlighted problems or just the ones we did in class?
We're only turning in what we've done in class, unless I assigned it as an on your own problem. Like if I wrote OYO next to it during class, then you're responsible for that too. Does that make sense?
Yes.
All right. So let's jump back into our handout. I gotta change this. And we're going to do more resonance problems, and then we're going to do a couple of functional group problems. Stop. Yeah, we stopped at one. We did 137. I think we did all of those. Did we not?
We can't see what you're talking about.
Oh,
We only did B and E on 137.
all right. 1 second, let me pull it up. We'll do a couple more of those, and then we're gonna go down and go ahead. I see 2 hands up.
I'm looking on my Blackboard. This is back to the module 1, but I'm looking on my Blackboard and you had like a skeletal assignment and I
Right.
don't see that. I only see the bonding, then just an area to turn in that assignment. I don't see the skeletal one.
Because you're gonna turn them all in the same link.
Yes, but I don't even see
You don't see the second assignment?
no.
I agree.
All right, hold up. Let me go back. It may just not be visible. I can fix that though. Yeah. All right, you'll be able to see it now. All right. Let me go back to here. All right. So somebody said we did B and which one? E? On 137?
Yeah, we've done B and E.
All right. Where I put that? All right, let's do one more of those. Let's do H, and I'm gonna make this one that you do yourself. So let's do H. Here and paste it. All right, so H, let me crop this right quick, sorry. All right, so come on, Russell, get your mind right. All right, so we need to put a pair of electrons here on carbon. So what do we need? Again, we're drawing resonance forms. What are we looking for?
A donor and acceptor.
Good. And they have to be what?
Adjacent.
They gotta be adjacent, next door to one another. So you see right here, this carbon is your donor, and it's adjacent to a pi bond, right? What system does that fall under?
Lytic anion.
Good, and a lytic anion. So how am I gonna push the electrons? Right, this is the donor, this is the acceptor. I'm always pushing towards the acceptor. All right. So that resonance form is going to look like like this. Double bond is not going to be here. Pair of electrons here, negative charge, next door to a carbonyl. Now, do you see that pattern again? The same type of pattern. Is that right? You got a pair of electrons on a carbon adjacent to a pi system.
Yes.
So what would the arrows look like in that case? Where would I start?
From the pi bonds.
Pi bond is tied up. The lone pairs are just sitting there. They're
You
more
use a
readily
pair.
accessible. So I'm gonna start here. This is gonna be my donor, and then the pi bond is gonna be my acceptor. Remember, we said if you had loose change in your hand versus a roll of money in your pocket, you spend the loose change first. So the lone pairs are like loose change. All right. So that's that. And then, so now the double bond is here, and then oxygen, sorry about that, it's here. And now that's negative. All right, so those are 3 resonance forms. And remember, we said that if you added up the donors and acceptors, that'll give you an approximation of how many resonance forms you'll have, right? So we got 1 donor, 2 acceptors, so we got 3 resonance forms. You okay with that? With that resonance? And then you can do C on your own. All right, questions about that? Is this clicking or is it not clicking?
Can you go back to what you were saying about figuring out how many resonance structures you have, like counting the donors and acceptors?
Yeah, so in the original structure, right, I got a pair of electrons that's going to be my donor. And then I have 2 pi bonds that can both act as acceptors. So to approximate how many resonance forms, because that's always a question. When do I stop? How do I know when I'm done? So to approximate the number of resonance forms, you can look at, add the donors and the acceptors up, and it'll give you an approximate number of structures that you should be able to get. So since I have one donor and 2 acceptors, then I should get 3 structures. And I did, right?
Yes, thank you.
Yeah, you're welcome. All
So-
right, go ahead.
Would the cation be an acceptor as well?
Yes,
Be one? Okay.
pi bonds and cations are acceptors, and lone pairs and pi bonds are donors. Because the whole concept of donation and accepting is based on you're talking about electrons. Right? So you donate electrons or you accept electrons. All right, let's do another example. We got A and C highlighted here. Which one do y'all want to do? Or you want to just do both?
Yeah, can we do both?
Can we do both?
Absolutely. Practice makes perfect. All right, so look at A. We don't have to cut this out. We could just put the arrows in. Look, and logically, a lot of this stuff is just logic. If you look at the left structure and the right structure, what happened? What changed? Once you figure out what changed, then it's just a matter of putting the arrows in to show how that change occurred. So what happened from the left to the right?
The lone pair on the carbon donated to created a pi bond.
Man, yes. And what else happened? See, because this part, go ahead.
I was going to say one of the bonds that connects the carbon and the nitrogen becomes a lone pair on the nitrogen.
Absolutely. You see how that works? Since this became a pi bond, and notice where my arrow's stopping, between the atoms, not somewhere off in space. That's very important that you learn arrow etiquette and put the arrows where they belong. So that going between those 2 atoms means I'm making a bond, a pi bond there, right here. And then the carbon that's highlighted in orange, if I don't do anything to it, it's gonna have too many bonds to it. So that forces this pair of electrons onto nitrogen. Are y'all following that? So do you see the logic behind that?
Yes.
Yeah. And then the nitrogen, if you have, sometimes you'll have a question where you don't have the charge shown, but you might have to calculate it. How do we calculate the charge on nitrogen? What's the little bootleg formula I gave you?
Valence minus actual.
So for nitrogen, the valence is 5. The actual is what? 1 from each bond, and then count the lone pairs up. So you got 4 from the lone pairs and 1 from each bond. So it's going to be 5 minus what?
6.
So that's how I get the charge of -1. All right, let's go ahead and do C. Oh, and that problem over there says locate all donors and acceptors. So where's my donor here in this problem on the left?
The CH.
Yep. So this is my donor. By default, the pi system over here becomes my acceptor. And that falls into the category of an allylic anion. It's a negative charge adjacent to a pi bond, right? That's why I gave you those patterns. If you find the pattern, the electron flow from that particular pattern never changes. So if you know how to push the electrons in an allylic system, then you'll always know how to do it. Doesn't matter what system you have, if you find that pattern, you can push the electrons. All right, let's go down to C. Let me put some lone pairs in because the book that I took these problems from, they don't believe in lone pairs. I'll swear by them. You gotta have them. It makes teaching part 1 way easier. So let's apply some logic. What happened? Going from left to right. Oh, let me put this through this too.
The pi bond gave electrons to the oxygen.
Okay, good. And then what else happened? Because that's right. That's one part of what happened, but what else happened?
CH gave his lone pairs to create a pi bond between
Good.
CH and C.
Good. So this happened, right? This happened here. Oh, sorry, wrong pen. Boom. Is that right? Uh-oh. Here. And then this happened here. Is that right?
Yes.
Yes.
What pattern does that follow? As you can see the pattern right here. You can see the 3 atoms here.
Is it a allylic anion?
It's a allylic anion. It follows that pattern. It's exactly right. All right, let's do 141. It says determine which ion is more stable. All right, and again, when we think about resonance, that's one of the factors that it contributes to is the stability of a cation or anion or even a radical. If we compare we compare those 2 structures, which one is able to do resonance? Can we do resonance on this one?
No.
Tell me why not. You're absolutely right.
Because you can't. Go ahead.
Go ahead.
Josh.
Oh, they're not adjacent to each other?
Yeah, that's right. This is your acceptor, right? Because it's a carbocation. And then the pi bond is your donor, but you got a gap between them. You see that? There's a gap between them. So they can't talk. If they can't overlap orbitals, they can't share electrons. So this is no resonance. Over here, see the difference? You see how the cation is now allylic and right next door to the pi bond?
Yes.
Compared to the other structure? This will be an example of an allylic cation. How would you push the arrows in this case? Because we haven't worked a lot of these, but how would you push the arrows in this case?
Would you put a lone pair in that crevice right there?
Well, in the case of an allylic cation, let me show you right quick, because we haven't talked about that a lot. But if I have an allylic cation like this, right, what happens in this case is that the pi bond simply shifts from one side to the other. There are no lone pairs involved. All right, this is just going to shift to here. And the pi bond is going to end up here. Following? So then the new structure is going to look like this. CH2, and then this is also CH2, but the plus charge is going here. All right. So for that allylic cation, the pi bond just shifts from one side to the other side. And again, that can't happen unless those orbitals all overlap, are able to overlap. And here, the orbitals actually look like this. They're all p orbitals. So you got a p orbital here, you got one here, you got one here. So that's why they're able to share electrons. All right, so if you go to here, what would you do with that? How would you show the resonance form? You do see the pattern, right? You would shift the electrons to here, right? And that would give us, oh, I got room out here. Praise the Lord. That would give us this. But now your plus charge would be on this carbon. And the reason it's on that carbon, what did I take away from that carbon by moving that pi bond up where I put it?
Electron.
I took electrons away from
Minis, I cannot fucking hear you, bro.
it. Anytime you take electrons away from an atom, it's going to become more positive or fully positive. All right, does that make sense? And here's another question. How many hydrogens are on that carbon right here? How many hydrogens would be there?
One.
One, good. So over here it's still there. But because it's skeletal, I don't have it shown, but there is one hydrogen here. That's why it's positive. I broke one bond to it. It had 3 bonds left, so it becomes a cation. All right. So now the original question is, which one is more stable? Is it the one that can do resonance or the one that can't do resonance?
The one that can do resonance.
Yeah, this is going to be more stable. Right? Resonance always offers stability. Anytime you can do resonance and delocalize a charge, which we did here by sharing it between switch pins, sharing it between this carbon right here and this carbon right here, right? That plus charge just oscillates between those two. And anytime we can take that charge and share it like that, then it's going to stabilize it. I always like to think back to that initial resonance video where you could take a load and share it among multiple people, right?
But I'm sorry for backtracking like this, but why
No, you're
can't the
good.
second one do resonance again?
Well, let's think about it. Okay, so if the pi bond is your donor, right?
Right.
If I push these electrons here, do they have anywhere to go? Like this carbon right here can't participate because it's not an acceptor. It's not positive, doesn't have another pi bond to it. So if I push those electrons from the pi bond where I have them shown with the arrow, that carbon that's circled is going to end up with too many bonds to it. So I have a donor, but I don't have an acceptor right next door to it. It's got the acceptor has to be adjacent.
Okay.
Yeah, if it's not adjacent, then they can't speak to one another.
All right. Thank you.
Yep, no problem. All right, let's look at E. And to do E, I'm gonna put a lone pair on nitrogen because it's there. What do you think for E? Which one can do resonance?
The first one.
The first one. The second one, it has an acceptor, but no donor. All right, it's got an acceptor, but it didn't have a donor. So the fact that it doesn't have a donor means it can't do resonance, because to do resonance, you need both donor and acceptor adjacent to one another. Right, and then over here.
There's no donor?
Okay, give me the two examples of donors that I gave you. Give me one of them. So a donor can either be a lone pair or it can be a pi bond. You following?
Yes.
So if there's no lone pair or pi bond adjacent to that carbocation, then it doesn't have anything that can give it some electrons to stabilize the charge. But over on the left side, you see nitrogen does have a lone pair, right? It can put that right there and make a pi bond. Is that right? And then I'll get this like that, and that nitrogen now becomes positive. And that's my resonance form. So of those two structures, which one do you think is the most stable?
The first one.
First one, because it can do resonance. And resonance always increases the stability of a molecule, right? And this system right here, it's the fourth system that we'll encounter, right? I said allylic anion, allylic cation, allylic radical, but this is an example of a 2-atom unit. It's not allylic, right? But it's a 2-atom unit with a donor and acceptor next to one another. All right. So that's the fourth type of scenario you'll encounter with resonance. You're either going to see allylic anion, allylic cation, allylic radical, or something like this, where the donor and acceptor are directly bonded to one another. And it's only 2 atoms and not 3, because all the allylic systems are made up of 3 atoms. And this is an example of a 2-atom unit or 2-atom system.
Where do you see the 2 atoms when you were saying that?
So it's carbon and nitrogen. You see how the nitrogen has the lone pair and the carbon has the charge? So this is your donor, and I'm sorry, this is your acceptor, and this is your donor. So this is an example of a 2-atom system. All your other patterns are 3-atom systems. All the allylic stuff is 3 atoms. See right here how this is 3 atoms? 1, 2, 3. All right, up here, when we did up here somewhere. Yeah, right there. Same thing, right? That's 1, 2, 3 atoms. Everything else that we've looked at have been 3 atom systems. And this one is a 2 atom system.
Are you saying that because you have the nitrogen as a donor and the carbon as the acceptor?
Yes. All right, any questions on those?
I have a question.
Go ahead.
Will there ever be a case where an analytic anion will be a 2 atom unit, or
No.
it will always be 3?
Yeah, it's got to be 3 because by definition, allylic means adjacent to a pi bond. And the pi bond is always going to be between 2 atoms, right? A double bond is going to be between 2 carbons or a carbon and some other atom, right? But the donor for the allylic anion is always some atom with a pair of electrons is going to be the 3rd atom in that system. Does that make sense?
It will always be the 3rd atom.
So if I have a system like this, let's say this is an NH2, right? This is the pi bond. This is the donor, and let me write the carbons in here, CH2. All right, that's 1, 2, 3 atoms. I can't have a pi bond without 2 carbons or two atoms to make it up, right? So a pi system is always going to be composed of 2 atoms.
Okay.
Good question. All right, let me erase that. All right, let's go to, we're going to come back to this part because I want to talk about these functional groups real quick. And we'll come back to here. All right, so because we only got 8 minutes left and I don't want to neglect functional groups. So right here, this is Taxol, and this is not extra credit, by the way. Or did I say that? Yeah, I did say, no mind. So we're going to go through this and then you'll just turn it in the extra credits slot. We got 34 out of 39, so 5 people are not here. So we got 34 beneficiaries. All right, so we're going to walk through Taxol. But before my wife passed away, this was the first drug that they gave her when she was diagnosed with breast cancer. So this is the synthesis of Taxol. Let me add that in as the extra credit part. Make it worth so. You can Google it, by the way. Actually, there were 2 groups. You're gonna find that there are 2 groups. But you need to answer that part. People must not know how it works. You're gonna answer that part before you turn this in. And this is in 1A, by the way. It says it says functional group extra credit. All right. So there were 2 groups that were working on this. One was at Florida State, another group at Harvard. Because the reason you have to have a molecule like this, why would you want to synthesize it? Well, the natural source of it is the yew tree, the Pacific yew tree. And it takes 100 years for one of those trees to grow. Right, it's actually from the bark of it. But out of the bark, you might only get 100 milligrams of Taxol from one tree. So that's barely enough. I mean, that's not really even enough to treat one patient. So you gotta have a way to make it in large amounts. right? So there were two groups competing to synthesize it. The group at Florida State, you got to find the name though. They finished it first, and they also licensed it to Bayer. I think it was Bayer or Bristol Myers. They licensed it. So every time Bristol Myers makes this and sells it to a chemotherapy clinic or a doctor's office or a hospital, the person who licensed it to them gets royalties off of that, right? Every time. All right. So with Taxol, this is a perfect example of a molecule where we have to find all the functional groups. And again, functionality goes hand in hand with function. So when you have a functional group, it's going to determine how certain things react, especially in the body. The functional groups actually dictate how things fit into certain receptors. If you watch the video, you saw where I was talking about THC, how it binds into certain receptors in the brain, how ecstasy, MDMA, binds into certain receptors in the brain, how morphine and heroin are almost identical. The exception happens when you take morphine. Sorry about that. When you take heroin, it's actually metabolized into morphine in the body. So it's only a difference of one functional group. So all that stuff matters. And if you notice also, let me point this out too. See how that's on a dash line and this is on a wedge line, that's on a dash line. That's what we call stereochemistry. That's the 3D orientation. But sometimes we get tricked into thinking that these molecules are flat because we only see them in 2D. But this molecule actually has a shape. And because of the shape, it can fit into the receptor in the cancer cell that is supposed to kill. It fits into that receptor and is taken up by the cell. The problem with chemotherapy, which has always been a problem, is sometimes regular cells also ingest the drug and they get destroyed too. So I don't know if you had anybody in your family that's experienced that, but I watched it firsthand with my mom and my wife. Thankfully, my mom survived. My wife did not, but I watched the side effects: fingertips turning black, feet under her feet turned black, all this stuff. So we had it has effects on good cells and bad cells. So that's why everything is moving now towards targeted therapies. But anyway, let's go in and pick out these functional groups. So we're going to start here. We're going to pick that out here, here, here. Let's start on that side. So what will we call this functional group? You don't know that, but I'm going to tell you. So pH is an abbreviation for a ring that looks like this, which we call what? Somebody tell me, because we saw this the other day.
Aromatic.
Good, excellent. It's an aromatic. So anytime you see pH, it's an abbreviation for aromatic ring, right? So we're just going to call that an aromatic. All right, what about OH? Just OH hanging out there by itself.
Aldehyde.
An aldehyde is a carbonyl.
And alcohol.
It's alcohol. See how it's just hanging out and it's just bonded to carbon. There's no carbonyls present. There's nothing else present except that OH is single bonded, has a single bond to carbon. What about up here? Now this is a carbonyl, but because of what it's bonded to, right? It's not just a carbonyl, it's a specific type of carbonyl. So what is it?
Is it an amide or amide?
Yes, excellent. Who was that?
Sonata.
Great. It's an amide. We call it amide. Yeah, but it's an amide, right? It's a carbonyl. This is what makes it an amide. It's the nitrogen bonded to the carbonyl right here, right? And the carbonyl actually, again, the type of carbonyl is going to be based on what's attached to that C double bond O bond, right? Because that carbon has two spaces on it. where it can attach stuff. See, let's look here. This is also a carbonyl, but it has an oxygen bound to it. Is that right? But that oxygen is not an OH, right? We call that oxygen, where it's an OC, that's a carbon right here. We call it an alkoxy. So if the carbonyl has an alkoxy group attached to it, what is it?
Is it a ketone?
No, a ketone will have carbons on either side. Just think about, well, y'all probably don't even watch Fred Sanford, but it's an ester. Let me change the color on that.
The one you circled is an ester, or the one next to it?
Say again, I can't hear you.
The one that you circled is an ester, or the one next to it?
No, the whole thing is an ester. The oxygen, let me change the color on that, because that's a great question. The oxygen is what distinguishes that carbonyl from everything else. So an ester would look like this. So you're gonna have the C double bond O, but it's gonna be O, R, or you'll have C double bond O, OH. Somebody hit me with this one the other day. This is what? Anybody?
Carboxyl.
It's a carboxylic acid. Good. All right. So we have an amide, an aromatic, an alcohol, and an ester on that side. Now let's go on this side. I'm gonna pick out a couple of these, and then we'll finish this up on Friday and move into, we'll do a couple of more examples from this part of the worksheet. I'm gonna assign some on your own stuff on this part. And then we're gonna move into intermolecular forces and physical properties and all that stuff. So right here, I'm gonna pick out here, here, let's do this here and here, because you at this point you know what an alcohol looks like, right? And we're gonna do this one because we got a couple of alcohols in there. All right, let's start here. What functional group is that? You have an oxygen with a single bond to carbon on either side of it with no double bonds.
Ether.
Good. Who was that?
Janelle.
Very good. It's pronounced ether, but you're absolutely right. All right, great. That's a very prevalent functional group, the ether functional group. So what about this one? And let me show you what the AC. This is what the AC group looks like. So in this case, the AC is bonded to oxygen. But sometimes it'll, but no, let me leave that alone. So this is acetyl group, right? This salamander keeps coming in my garage. I'm gonna have to do something about that. Okay, never mind. Y'all didn't hear that. I don't kill animals. All right, so it's an acetyl group, but when it's bonded to oxygen, we call it an acetate. See. But at any rate, what type of functional group is that? If it has an oxygen here and then a carbonyl right next door to
it. Ester.
It's an ester. Good. Excellent. Is this an ester also next door to it? You see the O?
Yes.
Yep, it is. If you see a carbonyl bound to oxygen like that, and that oxygen is not an OH, it's going to be an ester. All right, let's go up to here. What is that functional group? It's a
Is that an
carbonyl.
alcohol?
Okay, so carbonyl. So it can't be an alcohol because alcohol is just an OH, right? So it's a carbonyl, and it has a bond, the carbon on both sides.
Is
Right.
that a ketone?
It is.
Yeah.
It's a ketone, right? Make your flashcards with these functional groups. It's not on this test, but it's definitely on the second test. So make your flashcards and go through these things relentlessly. All right, there's only one more, and well, there's more, but right, we know that this is a alkene. It's just a double bond. Here, you see how you have two, and let me put in the CH3. So that's a CH3, and that's a CH3. But when you have two CH3s together like that on the same carbon, there's a special name we give that. We say that those are geminal. So we call it a geminal dimethyl. Right, but you can see right away, this is a very complex molecule. And the thing about it is that, you know, we talked about the stereochemistry. Let's see, there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 stereocenters in here, right? So that's 10 stereocenters, and they all have to match what you see right here. If one of those is off, then the efficacy of the drug is going to go down because it won't fit right into the receptor. That's how nuanced and how specific these things are, right? But we're going to stop here because we're out of time. We're way out of time, 6 minutes over. We'll stop here. We're going to come back. We're going to work through some of these on your own problems up here, a couple on Friday, and then we're going to start on the intermolecular forces and boiling point, melting point, physical properties, and all that stuff. And we'll be done with that, and then we'll start the second module, which is dealing with pKa. All right, so I'm gonna stop recording, stop sharing, all that stuff.